Okay, so today we're going to calculate angles between lines and intersection of lines given in parametric or vector form. So we're just going to review coming up with equations of lines from the other day. So first one, determine a vector equation of the line that passes through those 2 points. So remember, we need a position vector. So I'm going to call it P, sorry. I'm going to choose just one of the 2 points and make it a position vector. And then my direction vector, just a subtraction between those 2 points. So 6, -3, minus -2, 4. So that's going to be 8, -7. So now our vector equation are, which remember represents xy, vector xy, equals -2, 4 plus t times 8, -7. T is a real number. Okay? You could have any direction vector parallel to that. You could have other points. I would either choose this one or this one. Don't start calculating other points. Okay? Next one. So here we've got basically a general case. Put into parametric form means, you can keep the t at the beginning, but you can put the, actually, yeah, I'm just going to keep it like that. Y equals k plus tb. Those are your parametric forms. So it doesn't matter. You can switch these around. Really doesn't matter. But you're splitting it up into the x component and the y component. Cartesian form. So now from here, we want to solve for t, the parameter. So t will equal x minus h over a. This one here, t will equal y minus k over b. So in order for this to be true, this equation, the t values have to be the same. So that means x minus h over a equals y minus k over b. And that's the form that we keep it in. For sure, for 3 dimensions, this is 2 dimensions. So we'll keep it in that form. We might then ask you to show it in slope y-intercept form. You can rearrange that, or general form. Okay, but in this unit for vectors, this is fine. And certainly that's the only choice really when we get to 3 dimensions. Next one is our normal form that we're used to back from Math 10. And we're going to show it as a vector equation. So we need a point and a direction vector. So if you were to solve for y, to put it in slope y-intercept form, you're going to see what the slope is and what the y-intercept is. Let's use the y-intercept as our point. So that will be our position vector. So y-intercept is 0 for x, -5 for y, and then I'll use t. My direction vector, so the slope is rise over run. Remember, rise is your y, and run is your x. And then t is a real number. Okay? Now this next form, there's your xy, right, is your r, and the dot product with the normal vector, okay? Well, the normal n is representing the normal vector. That's the vector perpendicular to the line. So we know our slope from here is 4/3. So our slope perpendicular would be -3 over 4. Okay, so our normal vector, which is the vector perpendicular to the original. So the vector that represents this slope here. So the rise is -3. So that will be in the y component, and the run is 4. So now I'm going to use xy just to help us see how this works. 4 -3 equals to some constant. So if you take a look, if you take the dot product, you get 4x minus 3y. That's exactly what this says here. We need it to be equal to 15. Now, if you hadn't been given that original, how would you get the 15? Well, you could take, really the D is a position vector dot product with the normal vector. So if you take position vector 0, negative 5, dot product with 4, negative 3, you get 15. Okay, so just be aware of that. Okay, so next one, determine the equation of the line passing through 2, negative 5 that is perpendicular to 4, 7 as a vector equation. Okay, so perpendicular to 4, 7, so I'm just going to write it here, D perpendicular, because this, we could consider this to be D. So the line passing through perpendicular would be direction vector. We would switch the components and change the sign on one of them. So I'm going to make that 7 and this negative 4. Doesn't matter which one you make negative. Okay, so we're going to have R equals position vector. That point as a position vector will be 2, negative 5. And I'll just use T, 7, negative 4. Okay, and then really we should put T, element of the set of reals. Okay. All right, so this other form, so that normal vector form, we need the normal, so the perpendicular direction vector to the direction vector of our line. So this is our direction vector of our line. So perpendicular goes back to the original. Okay, so we'll have R dot 4, 7. And then, as I mentioned in the last question, to get that D, we need to, we just take the position vector, any position vector, in this case 2, negative 5, and then dot product with that normal vector. So that's going to be 8 minus 35 is negative 27. Okay. Then slope Y-intercept form. So you can just think about what the slope is. Oh, we want the line perpendicular to that. So we're going to look at our direction vector. So slope will compare to this direction vector here. So slope is rise over run. So that's going to be negative 4 over 7. So y equals negative 4 over 7x plus b. And we can use a point to help us figure out what b is. So that point, negative 5 for y. Computer is slow. All right, and so then b is, so negative 5 with the denominator of 7 is negative 35 plus 8 over 7. Okay, which is negative 27 over 7. Okay, now I went from the slope and used a point. From this, okay, you can convert it to general form. That's going to be, remember r is xy, so that's going to be 4x plus 7y equals negative 27. If I solve this for y, then I get negative 4 sevenths x minus 27 over 4. Okay? Oh, sorry, 27 over 7. Okay, which is exactly what I got here. I didn't show the final in this one, but there's your slope and there's your y-intercept, exactly what you got So you might find it easier. If you have to find the normal vector form, then it's easier just to solve for y. Okay, now we have a Cartesian equation of a line. It's 3 dimensions, obviously. We want to show it as a vector equation. So remember, to make this Cartesian equation, each part of this equals the parameter. So that means t equals x plus 2 over 3. T equals y minus 4 over 2. Gonna have to be patient with the computer. And t equals 3 minus z over 5. Okay, so now we're just going to rearrange to solve for x, y, and z. So you can maybe do this in your head. You're in Math 35. So that'll be 3t. You can put the t's first. I'm going to put the constant first because that's sort of relates back to a vector equation. So that's going to be negative 2 plus 3t. Y is going to be 4 plus 2t. And just be careful with the last one. Notice how z is negative. So z is going to be 3 minus 5t. I'm kind of running out of space here. So just going to put it down on the side. Okay, so now my vector equation. So the point, you look at all the constant terms. So negative 2, 4, 3 plus t times 3, 2, negative 5. Okay. Next one, we're given a line. Show that the point does not lie on the line. So you want to look at each component. So basically here, we want to see if 1, 2, negative 3 is equal to, and I'm going to show this line L in vector form. So that means I look for the constant terms, 1, 2, and then here would be 0, plus t times negative 1, 3, 2. Okay. So take each component of that. So x equals 1 minus t, and solve each of these for t. If the t's are all the same, then, because the t has to be consistent in each component, and if it's not, then it's not, that point d is not going to be a point on the line. So we're going to check, oops, I shouldn't put x, I should put 1. All right, so right away, I see that t has to be equal to 0 from the x component. Same, the next one, looks good. Actually, this is a great question because you can kind of tell already the x and y components are the same. But anyway, it's the process. We'll go through the formal process of doing this. So t equals, again, t will equal 0. So we're good so far. But now you can tell that it's not going to be a point because the z component is going to have a t value of negative 3 over 2. So this is very painfully slow. Okay. So then, determine the vector equation of the line. So a vector equation, actually, I should just put a vector equation because there's more than one possible, of the line parallel to line L that passes through D. So parallel means it has to have the same direction vector. And it goes through D, so now my position vector is 1, 2, -3. Maybe I'll call it S instead of T since it's in the same question. And then parallel, just use the same direction vector. Okay, and S element set of reals. Okay. Alrighty. Next one. Finding intercepts. So we know how to do that in Cartesian form. Y-intercept is when x is 0, x-intercept is when y is 0. Same thing here. So again, you can show in vector form or actually just show out in parametric form. That's going to be 12 plus 3t. That's going to be 6 minus 2t. Okay, so x-intercept is when y is 0. So I put 0 in for y, and I get t equals 3. So then to get the x-intercept, I have to put 3 in for t, and I get 21. Okay, so that's the x-intercept. Then y-intercept, that's when x equals 0. So now I'm going to put 0 in for x. And I will get t equals -4. So then y will be 6 minus 2 times -4, which is 8 and 6 is 14. Okay. Now, angles between lines. We've done angles between vectors. Now, it's the same deal, except we're looking, obviously, at the direction vectors. So if you think of having two lines, if it's in 2 dimensions and they're not parallel, then they're going to intersect, okay? And wherever your direction vector, you're looking, it doesn't matter if it's a big portion of it or a small portion of it, this direction vector and this direction vector, you're finding the angle in between them. If it happens to be going in the opposite direction in the negative, then it would give you this angle here, okay? And that's where the acute comes in. So if you're asked for acute and you get something that's obtuse, you subtract from 180 because remember that's a straight line, so they add to 180. So here it's 2 lines, they're not parallel, so they do intersect, so there will be an angle between them, okay? And we just use the direction vectors. So cos of theta equals the dot product of the 2 direction vectors over the magnitude of each. So actually, the magnitude of that one is 5, and the magnitude of that one is root 50. So, take the dot product, so that's -21 minus 4 is -25. And again, you don't have to simplify the radicals because you're just entering this into your calculator. We tend to, in vectors, deal in degree mode, so just make sure it's in degree mode. And then second cos, -25 divided by bracket 5 root 50, or you can use the fraction capability. If you do, just dividing, you'll need the brackets for the denominator. Okay, 135 degrees. So that is not acute. So that's a case where it's finding this angle in here. So we want to subtract from 180. So that's going to equal 45 degrees. And you would have noticed that it's going to be obtuse because the value there, negative 25, it's a negative. So if the value of the dot product is a negative, it's going to be an obtuse angle. Okay? So next one, notice that these are parallel. So what you have to check now is if they're parallel and distinct or exactly the same line. If they're exactly the same line, then the angle between them is 0. If they're parallel and distinct, then there's no angle between them. Okay, so how do you do that? That you want to check if this point lies on this line. Okay, so they're pretty close in coordinates, and if you think about it, well, it could be, I guess, because the y value is the same, the x is different, so could be horizontal, but then this is telling you that it's not. So you can basically tell that they're parallel and distinct by these particular coordinates, but some coordinates aren't going to be quite as obvious, so let's check it. So let's check if 2, negative 1 is a point on negative 2, negative 1 plus t times 3, negative 2. Okay, so this one's kind of obvious that it's not, but some won't be as obvious. So 2 equals negative t2 plus 3t, and solve each of these for t. So t is going to be 4/3. T here is going to be 0. Okay, so not the same, not equal. So therefore, lines are parallel and distinct. Therefore, no angle between them. We'll slow it down again here. Okay. Number 9, the Cartesian equation of line L is given. Show that the point P lies on line L, and then find the acute angle between that line and the line PQ. Okay, here's 10. So, because it's in Cartesian equation form, we don't have to really convert back to another form. We can substitute the x, y, and z in and make sure they're all equal. So when x equals, actually, I'll just show the whole point here. So we're going to have P 5, 8, 0. So if I substitute 5 in, I'm going to check if that's equal to 8 minus 7. Check if that's equal to 1 minus 0. Okay, so that's going to be 2 over 2, which is 1. That's 1. And that's 1. So yes, P is a point on L. Okay, so basically we've got a line in 3 dimensions. Okay, point P is on it. And then we want to find the angle between L and the line PQ, where Q is, say, some point over here. Okay. Now it says the line PQ, well, line going through PQ, right? It's going to extend forever. So we need the direction vector of our original line, and then direction vector, so direction vector of L there, and then direction vector of PQ. We can just subtract those position vectors of P and Q. Okay, so for L, direction vector, go back to your Cartesian equation. So the denominator there is 2, right? Remember, that's what you're dividing the coefficient of your parameter. goes underneath. This is a 1. And here, notice how that's opposite in sign. Really, that's the same as z minus 1 over negative 1. So if it's got a negative component or a negative term there, it means that the parameter has a value of negative 1 for the direction vector, I should say. So that's going to be your direction vector of L. Then PQ, so Q 2, 1, 3 minus P, which is 5, 8, 0. Okay, and now find the angle between those. Okay, so cos theta equals 2, 1, negative 1, dot product, negative 3, negative 7, 3, over 4, 5, 6, 18 and 49, 18 and 49 is 67, square rooted. Okay, so negative 6 minus 7 is negative 13. Minus 3 is negative 7, 16. Okay, and then calculator. Second cos. Should have cos in front here. Just a sec. Again, you know it's going to be obtuse. So acute will be 180 minus that. 37.1. Okay, intersection of two lines. So we want to determine the point of intersection. And so, again, in 2 dimensions, if they're not parallel, there will be a point of intersection. So remember, back to Math 10, point of intersection, the x value and the y value at the point of intersection will satisfy both equations. So we kind of want to remember that. So I'm just going to call this L1 and L2 for our lines. Yeah, you can convert them back to slope Y-intercept form or something like that, and then find the intersection, but fair bit of work, and we want to be able to do this for lines in 3 dimensions. So that's not going to work for lines in 3 dimensions. So we'll do the same process. So I'm just going to show each of these in parametric form. So 5 plus 2s and y equals negative 4 minus s. L2, x equals negative 5 minus 3t. Y equals 2 minus 2t. So if these lines intersect, they're not parallel, right? So you can take a look, not parallel. Then their x values have to be the same on each of the lines. So you can form 2 equations. So for x's, we'll have 5 plus 2s equals negative 5 minus 3t. For y's, we'll have negative 4 minus s equals 2 minus 2t. And actually, I'll simplify this a little bit. I'll get s's and t's on one side. And then solve that system. So here, I'm going to multiply this by 2. So my first equation, copy that out. out my second equation. And then I'm just going to add them together. So that goes away. 7t equals 2. So t equals 2/7. And then substitute them back in to get the point. Doesn't matter which line you put back in. I'm going to use in line this morning, so forgive me. L2, so that's going to be x minus 5 minus 3 times 2/7. X equals -5. Okay, so t is in L2. Oops. L2, so x equals -5 minus 3 times 2/7. So what's that going to be? That's -35 minus 6 is -41/7. Y equals 2 minus 2 times 2/7 is 14 minus 4 is 10/7. So the point of intersection is -41/7.